Okay, it's 5:30, so let's go ahead and get started today. All right, good evening, everybody. We're on our very last lecture, so thank you everyone for coming out. Looks like we have a little bit of a lighter crowd than we're used to. Right? So it's been a long semester to be sitting in front of the computer all the time. So first of all, let me say that I appreciate you guys kind of sticking it through to the end. I know I asked a lot of you guys for this semester, so reaching this point is it's really great, and I really appreciate I work that you guys put in. Okay? All right, so today I have a little bit of something a little bit special for you guys. So I thought a nice way to end this would be to talk about one of the cooler, in my opinion, of course, cooler applications for finite elements from a research point of view. And so I'm going to be talking a little bit about some of the research that I've done before. Particularly, about how do we use finite elements to model blood flow, right? And so what kinds of applications and what kind of problems are out there that can be solved with finite elements. So it's a little bit of a departure from what we've been doing in this class, because I think in this class we focus mostly on structural mechanics and also heat transfer for finite elements. But with this, I wanted to show you something that's interesting and maybe that you might not have thought of before on how to do finite elements. Okay, and so I'm going to do basically just a general overview of the methods that are involved with using finite elements to simulate blood flow, and then I'll go into maybe one or two of my own specific research projects around this. Okay? So ignore the date. So this presentation is a little bit old, and I just noticed it right now that I forgot to update the date. But this is we didn't go back in time, so it's still December of 2020. Okay? All right. So before we get rolling with that, are there any questions that I can answer before we get started? So hopefully everyone's still working on their projects. So I've been trying to answer questions as quickly as I can through email or through Discord. So as you run into issues with the code, definitely send me an email and I'll try to help you out as best I can. Okay. All right. So if there's no questions, we can go ahead and get started. So let me go ahead and full screen this guy. Okay. All right. So the title for this kind of workshop here is computational modeling of coronary blood flow. Okay? So it's a lot of words, but then we'll define basically each of them. But the key word that I want you guys to focus on with respect to this class is computational. Okay, because we know that from this class that the the whole point of doing finite elements is to give us kind of a platform to do computational engineering work. Okay, so first let's introduce, let's do a little bit of background introduction. So the focus for any kind of cardiovascular research is your cardiovascular system. So your cardiovascular system basically refers to your heart and the huge, vast network of blood vessels that kind of go out through the human body. Okay, and so on the right here, I have a figure of a guy. Looks like he's kind of waving hi to you, but I don't know if he realizes that he doesn't have any skin and bones. So he's a little bit maybe unaware of his situation. Okay? And so the purpose of the cardiovascular system actually, is just for transport. And so, all the various blood vessels throughout your body, you can almost think of them as like almost highways for your body to kind of transport goods. And so mainly, your body's gonna be transporting oxygen. So oxygen is a very essential element that's used for operating your muscles and for performing a lot of other functions in your body. And your blood's also responsible for transporting nutrients as well. So all the vitamins and all the energy and all the things that you obtain from your food, those are transported throughout your body through the cardiovascular system. So as you can imagine, your cardiovascular system is really, really important. Is someone have a question? I hear someone's mic is on right now.
It's white. If it was like a black sheet, I'd be like media or like gray or like light color. Yeah, it was like white.
All right. So I guess we'll be listening to TV too. Okay. And so, if you kind of draw the connection with our country, if we shut down all the highways and all the distribution centers in America, that would cause a really big thing. So it's the same thing with your cardiovascular system. Yes, good point. So let me go ahead and do that just now. Okay, there we go. Thanks for the tip. Right. Okay, and so it's really important for you to maintain your cardiovascular system through diet and exercise. So we've all kind of known this, right? Because you need to kind of maintain these highways in your body. And and one interesting trivia fact is that if you, took all your blood vessels and out of your body and kind of laid them side by side or end to end, you actually end up with 60,000 miles of blood vessels, or 100,000 kilometers. So that's kind of unbelievable when you think about it. In each person, you have that many blood vessels in your body. It's a little bit of an unbelievable fact, but it's true. So inside you, a normal human is that many blood vessels, which is kind of crazy to think about. Okay. And so, the reason we like to study this, not only engineers, but medical scientists as well, is that, cardiovascular disease is, still the leading cause of death worldwide. Okay? So I know COVID's kind of catching up to it a little bit, but but cardiovascular disease is still the #1 killer. Okay? And so, when we talk about disease, it's not only the cost of life, which obviously is the most important thing, but cardiovascular disease also places a big financial burden on the on our economy as well. So in terms of just caring for patients in hospitals, and also in terms of lost productivity, cardiovascular disease costs the U.S. about $500 billion each year, and this is a relatively old number too. So I think this was back in 2010, and so the trend for that is for those costs to only increase with time. So that cost is probably much higher now, maybe in the $600 or $700 billion range. And so there's a big interest from a lot of different fields to better understand cardiovascular disease and treatments, so that we can improve these outcomes. That we improve the death rate, but also improve kind of this financial impact as well. Okay, so what are some of the challenges? So relative to where we have been in terms of cardiovascular disease treatment, we've actually come a really, really long way. And so if you're ever bored one day and you want something interesting to look at, you can kind of read about or watch some videos about kind of how heart surgeries and were done in the past, and to see and to look at modern methods now and compared to where we have been, it's kind of remarkable how far we've come, right? And so there are some things where just to like when people perform open heart surgery, a lot of times they would just take your heart and throw it into like an ice bath to keep it to stop working, just so that they can operate on the heart. But we've come a long way since then. And so, but even then, there's still a tremendous amount of challenges and a tremendous room for improvement as well. Okay? But compared to other systems that we're used to working with in engineering, there's a lot of challenges that are unique to the cardiovascular system. Right. So one of the biggest challenges is that observations and measurements are really, really hard to obtain. Right? And so the thing is, with your blood vessels here, you have kind of a closed system, right? So if you look at just look at your own body, right? If you want to look at the blood flow that's going through your arm, you can't, because your skin is kind of in the way of it, right? And so to actually obtain these measurements and observations that we usually need, in order to perform engineering work, a lot of times you have to visit like a doctor's office, and they often have to stick some kind of probe inside of you, which is, not comfortable and also usually very expensive too. Right? And so this lack of data on how the cardiovascular system behaves is one of the biggest challenges, because it's hard to really design for something that you can't really take good measurements for, at least on a regular basis. Okay, and so that kind of leads us into this kind of unique niche that actually engineers can do to help, right? And so what's unique about engineers is that we actually already have technology that can simulate fluid flow, right? And so what I'm referring to, of course, is computational fluid dynamics, which is kind of an umbrella term for all different ways that computers can be used to simulate blood flow. Okay? And so originally, CFD has its origins in the aerospace industry, actually. And so it was used in the development for airplanes and rockets, because, back then, when you wanted to design like a new airplane wing, it was really expensive to build a prototype and to run experiments on that. And so simulation technology arose as kind of an alternative, so that you can design, your airplane wing on a computer without having to run a really expensive test. Okay. And so we can apply that same technology to blood flow, because blood is a fluid just like air, so it actually follows all the same conservation laws. So it follows the Navier-Stokes equations, it follows conservation of mass momentum, and so we can use that same software that we use for the aerospace industry and apply it in a biomedical context. Okay? And this actually gets us around kind of the primary challenge of working with the cardiovascular system that we talked about before, in that, you know, with simulations, we don't have to inject kind of invasive medical devices in order to measure things. We can just simulate them and get things like the velocity and pressure, you know, without having to run, you know, expensive tests. And so it's kind of interesting seeing kind of the development of this technology of both, you know, the aerospace industry and cardiovascular, because, you know, the problem is almost the same. Whereas, you know, it's expensive and it's usually time consuming or invasive, you know, to collect measurements or to collect data. And so simulations kind of provides an alternative to that, where you don't have to do all those kind of these things. Okay. Okay. And so the next thing I want to talk about is, you know, how do we actually perform this? How do we actually use this technology, or how do we actually run these simulations? And so, you know, I think, you know, when we're going over this, I think it's really useful to kind of contrast this with. Oh, was there a question?
Yeah, can you share your PowerPoint again?
Oh, sure. Oh, sorry. Didn't realize I was not sharing. Okay, can you ever see the PowerPoint again?
Yeah, thank you.
Okay, yeah, sorry about that. Yeah, technical difficulties. Okay, and so the question that we have is, or kind of relative to, you know, relative to, you know, what we use in ANSYS, the challenging part actually with cardiovascular simulations is obtaining the geometry, right? And so the way that we obtain it actually is through medical images. Okay? So what you see on the left right here is a typical CT scan or an MRI. So whenever you have a cardiovascular disease, you know, a doctor will scan you, you know, on a kind of a big kind of scary scanner, and they can actually see your blood vessels there. Okay, and so this is actually our starting point, because this kind of provides us a guideline for how to produce the geometry. Okay? And so after you load in the medical image data, the second step on the right here is to produce what we call the path lines. Okay? And so the path lines are actually going to be your centerline paths, you know, for all the vessels of interest. Right? And so the first step is to actually look at your medical image data, find all the blood vessels of interest to you. So if you look at this image right here, this kind of big chunky vessel right here in the middle, this big white thing, that's your aorta. So that's actually going to be your biggest blood vessel. And so the first step is to actually draw a line in 3D to actually, you know, that goes right down the center of that vessel. Okay. And we do that for all the vessels of interest right here. So you can see here I have kind of all the path lines for all the different blood vessels that we're interested in solving for. Okay, so the next step is a step called segmentation. And so in this step, what we're doing is once we've drawn the path lines, we can then follow those path lines along those, and then basically trace out the cross-sectional area for the blood vessels along those path lines. Okay? And so that's what we have here for all the circles. So what I did here was I basically followed the path lines, and then along each point or along each path line, I went to certain locations and I basically drew out, you know, the cross-sectional area for those vessels. Okay, and so you can see if you do that for all the vessels, you have kind of a series of all these little rings that define basically all the vessels that you want to simulate. Okay. And so once you're done with the segmentation, the next step is what's called lofting. So this step is kind of like almost like a three-dimensional connect the dots, where we take all of our rings together and then we connect all of them together to form just one kind of solid object. And that's kind of the result right here. Okay. And so once we're done lofting, then the next step is a step that you hopefully should be familiar with, is to actually mesh the domain. Okay. And so once we've obtained the geometry here from the lofting step, you know, from here we basically follow the same process which we follow for finite elements. So first we mesh the domain. So you can see here I've replaced this entire domain with a collection of you know, finite elements. So in this case I've used all tetrahedral elements. Right? Oh, question in the chat. Right. Oh, question. So how was I able to obtain the cross-sectional area? Is it based on the flow at the boundary conditions? Yeah, that's a good question. So the cross-sectional areas were obtained from the image data right here, actually. Right? And so we can still load the image data. And then what we're doing basically is if we follow the path lines along, then what we obtain is basically just a we kind of slice the image data at those locations in the path line, what we get is kind of a two-dimensional image of what that vessel actually looks like. And so actually, let me pull up a figure here just so you can kind of see. So it looks something like this, actually. So this is actually a screenshot from the software. And so what you can see here is that the on this this yellow line right here is kind of the center line path that I was talking about. And if you can follow that along, you can kind of get a snapshot of the vessel perpendicular to that path line. And then what you can do from there, you can basically manually draw out the cross-sectional areas. And these kind of circles here form the segmentations for our lofting procedure. Yeah, so you're using the same image data for both. So it's just you kind of do it in kind of two steps. So in the first step, we draw these centerline paths just to kind of give us a way to show us where our vessels are. And then from there, we manually kind of trace out the cross-sectional areas from this using the same image data. Okay. And so after we obtain the mesh, and so in this case, I use tetrahedral elements because the geometry is very, not very standard. And so, we have to use tets for this, right? And so after we obtain the tetrahedral mesh, then we apply our boundary conditions, right? And so here we're going to apply our Dirichlet and Neumann boundary conditions, kind of just like as we had before, right? And then from there, we just run the simulation. And so from there, we can obtain things like the pressure field and the velocity field, and then we can use these to perform any kind of research or analysis that we want, okay? So are there any questions on this so far? Okay. Okay, so maybe I'll keep it this view because I think it's easier for me to see the chat like this. Okay. And so that's kind of just the general process of how to obtain the simulation. So so you can see, it has a lot of similarities to our finite element process that we've seen so far. It's just obtaining the geometry is a little bit more involved because we have to do that based on medical image data. So it's not created in a standard CAD software. So we have to do it a little bit special. Okay. And so the next thing I want to cover is this idea of what's called lump parameter modeling. Okay, and so the whole idea with lump parameter modeling is to instead of running a three-dimensional finite element simulation, what we can do instead is we can use kind of lower order circuit elements. And so we basically leverage this this analogy between fluid mechanics and circuits to create kind of a much simpler model. And so, the question I think to ask, or a fair question to ask is, why would we even want to do this? And so if we can obtain a three-dimensional model of our blood vessels, why would we want to dumb this down and make it turn into a circuit instead, right? And so the reason for that is that it's, right now, it's just not practically feasible to simulate every single blood vessel in a person's body, right? So just like we talked about at the beginning, each person has 60,000 miles of blood vessels in their body. And so right now, we just don't have the computational power to simulate 60,000 miles of blood vessels, and have it finished within this century. And so we have to do a lot of approximations in order to run these simulations, right? And so, I think this image right here is actually a pretty good indicator where, you can see here we've simulated some blood vessels, but this is not the entire person's body, right? So, in reality, a person has much more blood vessels that extend far beyond this domain right here, okay? So we don't want to simulate all of that just because it's not practically feasible, but we do still want to, get the kind of the net effects of all of those downstream vessels. And so the way that we can do that is we can use what's called lump parameter modeling, okay? And so when we're doing this analogy here, we kind of have to make a one-to-one comparison of the various circuit elements and what kind of fluid mechanical effects that they have, on a typical blood vessel. Okay, and so the most common one that you see is a resistor, the humble electric resistor. And so what that represents in terms of fluid mechanics is viscous friction. Okay, and so what that means is that as fluid flows through a pipe, there's going to be some frictional forces that kind of sap energy away from the fluid, and the resistor kind of models that kind of perfectly. Okay, the next circuit element is a capacitor. So this is probably the next most common one. So if you're familiar with circuits, you'll know that the capacitor is responsible for kind of storing charge, right? And so the same thing can be said for fluid mechanics capacitors as well. And so a fluid capacitor is responsible for storing charge a little bit, okay, or storing flow, I should say. And so what effect that models in a cardiovascular system is what's called wall deformation. Okay? And so what's unique about your blood vessels is that they're basically flexible tubes. And so as you flow blood in them, they can expand a little bit to kind of locally store flow, right? And so we can model that with circuits using a capacitor. Right? And so the last most common circuit element that you'll see is an inductor. Okay? And an inductor models fluid inertia. Okay, so those aren't as common, but those are used sometimes. Okay. And then what you can do from here is that you can, once you have your circuit, you can solve those circuits for pressure and flow. And then what you can do is you can use those as boundary. You can actually use those as boundary conditions for your three-dimensional model. Okay. And we'll come back to this a little bit later, but I just want to introduce the idea of lump parameter modeling here. Okay. Okay. And so let's talk about the 3D simulations a little bit more. Okay. And so, anytime we have a finite element situation, we have to have our governing differential equation, right? And so like the one that you're doing for your projects is the heat equation, given by the formula that I have in the project specs, right? But for fluid flow, the formula that they follow is the Navier-Stokes equations, okay? And so the Navier-Stokes, if you kind of remember from your past fluids class, these define the conservation of mass and momentum for a flowing fluid, okay? And another thing that's really important for fluids is to define what's called the stress-strain relationship. Okay, and so most fluids we assume are Newtonian, and so that basically means that there's a linear relationship between shear stress and the velocity gradient. And so even though blood is technically not a Newtonian fluid, most of the time we just assume that it is because it's a lot easier to simulate Newtonian fluids than not. Okay, because if we don't assume it's Newtonian, then our Navier-Stokes equations don't actually look like this. So they look a little bit more complicated. Okay? And so the reason blood is not a Newtonian fluid is because they have this behavior which is known as shear thinning. Okay, and so what that means is that if you apply a lot of shear stress on blood, its viscosity actually goes down. Okay. And this is actually really important for blood vessels because when your blood flows through your very tiniest blood vessels, known as your capillaries, the blood needs to be able to kind of squeeze through those tiny capillaries in order to perform its work. And so if the blood wasn't shear thinning, it wouldn't be able to squeeze through those capillaries, and you get blood that's kind of stuck, into your vessels, which is not a good thing. Okay. But we only observe that shear thinning fluid at the very smallest length scale, so only in the very, very tiny capillaries. And most of the time we can't even see those anyway in the medical image data. So when you're performing the simulations, most of the time you're doing it in the fairly large vessels. And so for fairly large vessels, you can assume that the flow is Newtonian, and that's usually a pretty decent approximation. Okay. Okay. And so now we get to, the part of, how do we actually model these things, right? And so the way that we actually solve our Navier-Stokes equations is with the finite element method, right? So, I'm sure we're all familiar with that now. Right? And so, like we talked about, the finite element method, it just provides a discretization scheme, okay? And so just like we've done for, every other thing in this class, we have to provide a mesh, right? And so what the mesh is going to do is it's going to convert our partial differential equation in Navier-Stokes into a system of algebraic equations, right? And so, we've done that kind of ad nauseum in this class where we've produced our global linear system, right? And that's a direct result of the finite element method. So instead of solving a PDE, instead we're solving a very big matrix system, which is, much easier to do, okay? And so, that's kind of the purpose of that, okay? And so for this blood flow modeling, finite elements is actually the most common method to do this, right? And so if you're kind of familiar with the world of CFD, there's actually a lot of different methods out there to solving the Navier-Stokes. And so what's actually more common outside of this particular field is actually to use a method known as the finite volume method. And so the finite volume method is a method that's really nice for fluids, because it's a method that's conserving. And so that means that conservation of mass is kind of automatically preserved for that, or satisfied. And so, but for blood flow, where we have all these kind of really wonky and kind of strange geometries, finite elements are actually really a lot easier, right? And so the reason for that is with finite elements, we have this method called, the isoparametric method, the one that, you guys are all working on for the project, right? And the thing with isoparametrics is that you can take an element that's very kind of, strangely organized, right? So we have a tetrahedron that's kind of arbitrarily oriented. We can always map that back into a parent element where, all the shape functions always look the same, okay? And so the thing is with blood flow simulations, because our geometries are so wonky, we end up with tetrahedrons that look very strange kind of all throughout the domain, right? And so because finite elements has this isoparametric approach where we can always map it to something standard, finite elements is actually a really great method to use whenever you have kind of weird and wonky geometries like this, okay? And so in this case, it serves us really, really well, okay? Okay. And so the last point on this slide, you guys are all familiar with. So when we solve the finite element equations, we know that it's based off the weak form of the PDE. Okay, so we do the weak form instead of the strong form. Okay, and so next thing I want to talk about the different boundary conditions. But before that, are there any questions I can answer? Okay. All right, so let's talk boundary conditions. So, fluids equations are, very similar to all the other equations that we've done in this class. So we have our Dirichlet and Neumann boundary conditions. But how we interpret the Dirichlet and Neumann boundary conditions are a little bit different for fluid simulations, okay? And so let's start with Dirichlet, because Dirichlet is always the simplest thing to start with. And so remember, our definition for Dirichlet is, we're directly going to specify our solution parameters. And so for our structural simulations that we've done with beams and frames, in those situations, our Dirichlet boundary conditions were just fixed constraints. And so in those conditions, we directly specify the displacement at a particular nodes. Okay? And then for the heat equation, our main solution variable is our temperature, right? And so that's what you're working on for your project. So our Dirichlet boundary conditions are directly specifying temperatures on specific edges in our domain. Okay. And so for Navier-Stokes, our primary solution variable is actually the velocity for the fluid. Okay? And so any Dirichlet boundary condition means a direct specification of velocity on our mesh. Okay. And so that's usually the form that it takes for fluid simulations. Okay. And so typically you use Dirichlet boundary conditions on your inflow boundary conditions. Okay. And so that's what I've kind of shown you right here on this figure on the right. So in here, basically we have an inlet. So, the flow is entering the domain from the left. And so here would be actually a great location to input a Dirichlet boundary condition, okay? And so this is nice because this basically allows us to specify how much mass flow is going to be entering our domain, which is always going to be an important parameter. So how much mass flow or how much volumetric flow is entering your domain, okay? Okay. And so, just like our other cases, we also have a Neumann boundary condition. Okay? And so the Neumann boundary condition actually takes a similar form to our structural mechanics problems. And so Neumann boundary conditions usually take the form of a pressure for fluid mechanics simulations. Okay? And so a pressure is essentially a stress. And so a stress is a force divided by area. And so if you go back to our structural simulations with beams and frames, you know that our Neumann boundary conditions were either a force or a moment. Okay, and so the fluid mechanical equivalent of that is a pressure. Okay, and so that's how we supply our Neumann boundary conditions. Okay. Right. Oh, and these are often common for outflow boundary conditions, and the reason for that is oftentimes when we run fluid mechanics, we know we have some measure of what's the pressure on the backside of our domain, right? So oftentimes the term for that is back pressure. And so kind of the natural way to apply that back pressure is as a Neumann boundary condition on our simulation. Okay, and so those are kind of the two most standard boundary conditions for fluid simulations. And so if you say you're using ANSYS to run a fluid simulation, a flow boundary condition or a pressure boundary condition, those are going to be your most common. But we also have some specialized boundary conditions that we can use for cardiovascular simulations. Okay? And so think back, if you kind of remember from earlier in this talk, we talked about the lump parameter method. And so in those, under that method, we can use circuit elements to basically, approximate the behavior of all the downstream vessels. Okay? And so the most simple form for a lump parameter boundary condition is an outlet resistance. Okay? So this is actually kind of a spin-off the Neumann pressure boundary condition that we talked about previously. But an outlet resistance basically will supply a pressure on our domain, but the pressure magnitude is going to be a product of the flow and the resistance. Okay, and so we basically leverage an equation that looks very similar to Ohm's law. And so if you remember, your Ohm's law equation was voltage is equal to current times resistance. And so kind of the fluid mechanical analogy to that is pressure is equal to flow times R. Okay, and so the way these boundary conditions work is that as your simulation is running, it computes the amount of flow that's going through your outlet, just by integrating the velocities, and then it then multiplies that flow by the resistance, and then that gives you a pressure that you can apply as a Neumann boundary condition. Okay, and so these are very commonly used in our cardiovascular simulations, because what they model or what they simulate is the effect of the capillaries on the on our 3D simulation. Okay, because the capillaries they have a lot of viscous resistance because their diameters are really small. And that's going to create a lot of pressure that must be accounted for in your 3D simulation. Okay, and so the next, kind of more advanced boundary condition that you can do is a Windkessel model. And so this is kind of a derivative of our outlet resistance, but instead of just a single resistance, what we have is two resistors and a capacitor. Okay, and so this is obviously a little bit more complex because we have three circuit elements here. But usually gives you a more realistic product because the addition of the capacitor here allows us to model a deforming blood vessel. Okay, and so this can basically take into account the fact that all your downstream vessels can expand and contract and locally store blood. Okay, and so this will give you a little bit more of an accurate result than your resistance, especially in the case when you have an unsteady simulation. Okay. But just by being a little bit more complicated, it's a little bit more computationally challenging to model, especially if you're kind of coding it yourself. Okay, and so those are all the outlet boundary conditions. I also want to talk about the boundary conditions that we have to specify on the walls. Okay, and so by walls I mean basically the lateral surface of the vessels. Okay, and so the most common condition that we see here is called a rigid wall condition. Okay. And so what this basically specifies is that the velocity of the fluid as it touches the wall has to equal to 0. Okay, and so what we're saying is that the walls are not moving, and that any fluid touching the wall also has 0 velocity. Okay, so this is the simplest boundary condition, and so you can almost think of it as like a fixed constraint that we used for our frame and beam code before. Okay, and so all we're basically doing is we're saying in our gigantic matrix for our simulation results, we say that any node that touches the wall, their velocity has to be set equal to 0. Okay. Okay. And kind of the most common name for this is a no-slip boundary condition because the fluid cannot slip at the walls. Okay. Okay. And so that's kind of the most basic form for the wall boundary conditions. Kind of one step up from this is a deforming wall boundary conditions. Okay. And so just like we talked about before, blood vessels are not rigid structures. They actually, have some flexibility to them, right? And so to model this, we have to include capabilities for this in the simulation, okay? And so the way we do this is with a deformable wall simulation, right? And so as you can imagine, this is a lot more accurate than your rigid wall simulations, but computationally, it's often really, really expensive, okay? And so I think, this term has kind of been thrown around a little bit in this class, but this would be an example of what's called a multi-physics simulation, okay? And so by multi-physics, what I mean is that you're solving basically several different, governing equations at the same time, right? And so for deforming wall, you not only need to solve the Navier-Stokes equations for fluids, but you also need to solve the equations for solid mechanics for the vessel wall too. Okay, so since you're solving kind of two sets of differential equations, we call these methods multiphysics. Okay, and the interesting thing with deformable wall simulations is that there's you know, a lot of different methods available for performing this. So there's not just one way to do this. So, you know, there's actually varying amounts of methods depending on how much fidelity that you want, right? And so you can do kind of something that's relatively cheap, that gives you kind of the basic wall motion, but it's not going to be that accurate. And then from there, there's more and more complex models and more expensive models that you can do to model this this deforming behavior. Okay? And actually, this was kind of the subject for one of my research projects that, you know, probably that I think I'll probably get enough time to talk about today, where I compared different methods for performing this deformable wall simulation. Because it's a question that a lot of people ask all the time. You know, when you're simulating these things, you know, it's always fair to ask, you know, what method should I use, and what conditions should I use for this, right? It's the same as you guys, you know, when you're running ANSYS and you ask yourself, you know, what kind of mesh do I want for this? How big do my elements want to be, and what kind of boundary conditions should I apply, right? And so the choice of whether to use a deformable wall and you know, which deformable wall model that you want to use is just as important of a choice as any of those other things. Okay. Okay. Are there any questions on this so far? Okay. Okay. And so the next thing I want to talk about is time integration. And so, you know, we didn't get to do this in this class, but actually, you know, finite elements can actually be used for unsteady problems as well. Okay? And so actually, you know, everything that we've been doing in this class is a steady problem. So we basically are just solving the systems until static equilibrium. But a lot of phenomenon out there in the world are actually unsteady. So that means they actually change with time. And so you can actually simulate these phenomenon in finite elements, so whether in ANSYS or, you know, in your own codes. But in order to do that, we need a scheme in order to perform that. Okay. And so there's lots of different schemes out there in order to perform these time integrations, or time marching is another name for them. But the one that's often used with finite elements is a method called the generalized-alpha method. Okay. And so I won't get into the details about this method, because that kind of requires, you know, a few weeks of lectures in order to talk about. But the nice thing about this method is that it may not be the most accurate out there, but it gives a really nice compromise between stability, cost, and accuracy. Right? And so it's just a very nice method, because it satisfies kind of a lot of things while being, you know, relatively reasonable in cost. Okay. All right, so let's talk a little bit about, you know, some of the outputs that we expect from our simulation. Okay, so this is basically the step of you know, we've run the simulation, and, you know, and we want to take a look at our results, and we want to use them for something useful. Okay. All right, so the first output that is often looked at is flow. Okay, and so by flow, what I mean is either mass flow rate or volumetric flow rate. Okay. And this is kind of the first piece of useful information that we can obtain. And so the reason this is useful is because, you know, whenever you have a system like blood flow, where you have, you know, lots of different vessels and lots of different outlets, it's often interesting for doctors to see, you know, how much flow is going to this part of the body, right? And so if you have kind of a model that looks like this, so these blood vessels right here that you see kind of up top at these little tendrils, you know, the blood that goes through these vessels are going to go to basically the head and the arms. Okay. And so it's often useful for doctors to say, you know, how much blood, or what percentage of your blood flow is going to your head and your arms relative to like your legs and your torso. Okay. And so the flow is often one of the first things that is, you know, that's useful, especially for geometries with lots of different branches. Okay. And so the second useful quantity that we often look at is the pressure. Okay. So this is, you know, basically your blood pressure, right? And so, you know, there's a reason, you know, you can go to like CVS, and maybe not nowadays, but, you know, before you can go to CVS and measure your blood pressure, because it's a really important indicator for your cardiovascular health. Okay? And so, you know, high blood pressure is often a health risk, right? And so that's obviously something important to know. But there can also be, you know, a lot of other small things that can happen. So if you have kind of small pockets of high blood pressure in your body, you know, that could be interesting for doctors to know as well. Okay. And so, you know, one other thing that doctors can use with blood pressure is to measure kind of the severity of a disease. Okay. And so what I have in the top right corner here is kind of a simple example of a disease in this blood vessel. Okay, and so it's a little bit hard to see, but you can but from here you can see, you know, these parts that are highlighted in orange. What you have is plaque that's building up in that blood vessel, and it's restricting the amount of blood flow that can go there. Okay, and so what doctors typically do to measure, you know, how bad this disease is they actually measure the pressure drop across the disease. Okay. And so they have this device here called a catheter, okay? And what the catheter is going to do is it's going to measure your blood pressure before the disease, so that's known as your proximal blood pressure. And then they're going to measure the same blood pressure after the disease, and they call that your distal blood pressure, okay? And then they can, from there, they can take the ratio of these two things and call it a quantity called FFR, which stands for your fractional flow reserve, okay? And so from the fractional flow reserve, you know, they can tell how bad your disease is, because if this FFR is something like, you know, if it's something like 0.6, then what that tells you is that, you know, you had a 40% pressure drop going across this disease, okay? And that's something that's really severe. And so that's something that you know, that tells the doctors that they might need to perform surgery or perform some kind of intervention to alleviate that disease. Okay. The nice thing about simulations is that you can actually compute that pressure drop, you know, without having to stick a wire into someone, right? And so the thing with the catheter is that it's literally a wire that they often stick into your body. So actually, you know, the most common entry point is actually your groin. And so, you know, if doctors actually want to measure how bad your disease is, oftentimes they have to kind of put you under some anesthetic and, you know, puncture a hole into your groin and actually stick a wire up there. And the wire from there is going to snake around your body and go to some part of your where you have disease. So it's not the most comfortable thing in the world, although most people don't feel it because they're asleep. But most importantly, it's expensive because, you know, you have to go to the hospital and they have to put you under, you know, and in knowing healthcare in America, you know, your insurance is probably not going to cover that. So, you know, a lot of times you have to pay that yourself, which is, you know, a lot of times that's often a lot more painful than the surgery itself. And so the nice thing about simulations is that you can actually, you know, compute this thing without having to do an invasive, expensive procedure. So that's kind of one of the nice things about that. Okay. And so another quantity that's often measured in these simulations is the wall shear stress. Okay. And so what I mean by this is the wall shear stress is basically the amount of frictional force that the blood imparts onto your vessel wall. Because as the blood kind of flows past, you know, there's going to be some kind of shearing that results. So, like, you know, there's going to be some friction forces that result there. Okay. And oftentimes this wall shear stress is a big trigger for things like cardiovascular disease. Okay. And so it has a, you know, a lot of intense kind of clinical interest. And so this is actually one of the really big benefits of running simulation, because oftentimes it's really difficult to measure this in a person, right? Like, you're talking about, you know, forces that are being applied onto, you know, blood vessels that are really tiny. And so it's just not practical a lot of times to insert like a force meter into a person's body, right? And so kind of before simulations came around, you know, doctors kind of measured the wall shear stress just kind of loosely based on the velocity that they saw, but it was never really that accurate. And so the nice thing about simulations is that we can actually, you know, simulate this wall shear stress, and you're going to get a very nice and accurate number that you wouldn't be able to obtain otherwise, you know, with kind of standard measurements. Okay? And so just like I mentioned before, you know, viscous wall shear stress, it drives a lot of cell behavior, which can trigger things like vessel rupture or, you know, the formation of an aneurysm. Okay? And so an aneurysm is kind of just a kind of a sac of blood that kind of forms in your cardiovascular system. Okay, and so I think this is the last one. Oh, not the last one. But another output that's interesting for doctors to know is something called residence time. Okay, and so residence time is basically measures how long the blood stays stagnant within a certain area. Okay, and so it's literally, you know, how long the blood stays resident in a certain area, right? Because what can happen sometimes is that you might have kind of these small pockets of blood that form in your blood vessels. Right? Is there a question? Okay. And oftentimes these areas of kind of circulating and stagnant blood can cause a lot of problems, okay? And so oftentimes it's interesting for doctors to know, you know, how bad or how long the blood is staying right here, okay? Because the thing is, when blood kind of stays in one place, it tends to clot, or it tends to coagulate, so it turns, you know, solid, right? And so coagulation is basically the process of, that's what basically heals your wounds, right? So if you cut yourself, right, then blood is going to come gushing out. And then what happens if you kind of, apply pressure on that wound, it causes the blood in that wound area to become stagnant, and it becomes hardened from there, right? And so, that's great when you have a wound, but you don't want that happening within, your typical blood vessels, because, you want your blood to kind of flow freely, okay? And so one way that doctors can measure this is with residence time, okay? And so it's not the best indicator for blood clotting or coagulation, because, coagulation is actually a very complicated process that follows its own set of equations. But residence time can be kind of one indicator that tells doctors that, maybe we need to look at this area because blood is kind of staying stagnant in there for a really long time. Okay. And so, just like wall shear stress, simulations can compute this residence time really easily. Okay. Okay. And so the next quantity that we'll look at is the wall strain. And so this in particular measures, how much your vessel wall is stretching, basically, right? And so as your blood flows and as your heart pumps, your blood vessels are going to expand and contract because they're kind of stretchy things, right? And so how much it's stretching, that's often, a thing of a quantity of clinical interest, right? Because if your vessel is stretching too much, that can be, a cause for concern. Or if your vessel isn't stretching enough, that's also, a cause for concern as well. Okay? And just like all the other quantities, you can measure this with simulations really well, right? But the thing is, if you are interested in the wall strain, you have to run a deformable wall simulation. So you can't obtain wall strain for a rigid wall, because for a rigid wall, your vessel walls just aren't moving at all. Okay. And so that covers basically all the main, the main outputs that you can obtain from these cardiovascular simulations. So are there any questions on this so far? Okay. All right. So let's talk about some applications. Okay? And so all we've done up to this point is kind of just gone over just the theory and kind of the general methods for these cardiovascular simulations. But let's talk about how people actually use this in practice. Okay. And so the first area that's used is for disease research. Okay. And so with simulations, it opens up a wide range of possibilities for how we can actually study the cardiovascular system, because now all of a sudden we can measure things like the wall shear stress, we can measure things like residence time, and even things like pressure and velocity, which which we can obtain, but are not the easiest things to get, because we have to stick probes into people, right? And so with simulations, we can obtain these a lot more easily. Okay? And so with all this extra data, we can actually use this to study cardiovascular disease, right? So we can study things like what's the exact mechanism for plaque building up on the vessel walls, right? Or what's the exact mechanism that leads to stroke and things like that, right? Because before, a lot of times we kind of see the results of these happening, right? And so we see, someone get cardiovascular disease, and you can take a scan, but oftentimes by the time the scan is there, it's often too late because the vessel has already become significantly diseased, right? But with simulations, what we can do is we can simulate that entire process of taking a relatively healthy blood vessel and then the plaque kind of building up on those vessel walls, right? So that's never been seen before, at least not in a realistic geometry. Okay. And so this as you can imagine, this opens up the possibility for a lot of different disease research. Okay? And so what I've shown on the right here is actually a company that's dedicated completely to this, right? And so this company is called HeartFlow. So it's actually one of the only companies that's dedicated to this. And what they do is they run simulations to study, how severe cardiovascular coronary artery disease is. Okay? And so coronary artery disease, that's the disease that often leads to heart attacks. And so what HeartFlow aims to do is that it aims to use simulations to basically catch some of these cases early. So, if someone is at risk of heart attacks, HeartFlow can basically detect this a lot earlier. And then so doctors can actually go in and intervene before, a patient has potentially a life-threatening heart attack, right? And so it's really cool stuff because it uses this, it uses methods that we talked about in this presentation, and it uses it to solve, you know, a very real problem, right? Okay, and so the next common application area is in the design of medical devices. Okay, and so this is kind of a very engineering kind of application. And so just like we use CAD, like SolidWorks and ANSYS, to design you know, our engineering structures or engineering devices, you know, we can use CFD to design medical devices in basically the same way. Okay, and so what we can do is we can make CAD geometries for our medical devices of interest, and then run simulations on that to see how they perform, right? And so, you know, just like we've seen for like in the aerospace industry, or, you know, for every other ones, these simulations can take the place of, you know, very expensive prototypes and very expensive tests. Okay, and this is especially useful in the biomedical field because, you know, running experiments with like real human subjects can be very costly, and, you know, they can carry a lot of risk too. So, you know, being able to simulate these on a virtual platform is very, very useful. And the last, you know, the last application area that I'll talk about that's, you know, really exciting is actually in virtual surgery, right? And so, you know, because, you know, we're doing simulations and all of it's kind of virtual, you can kind of try things on these geometries that you wouldn't normally try on a real person, right? And so one thing is to try out new surgeries, right? And so, you know, say, you know, a doctor, you know, a surgeon, you know, wants to try out a new different kind of surgery, you know, on a particular kind of patient, right? And so nowadays, because, you know, we're a lot more conservative in how we test things on real people, you know, I think 99.9% of people would not be that excited to say, you know, a surgeon come up to them and is like, hey, you know, I know you're sick, you know, and we have this surgery that works pretty well, but I kind of want to try something new on you, you know, just to see if it'll work or not, you know. And I think most people will be like, hell no, you know, don't use me as your guinea pig, right? You know, this is my life that you're dealing with. And so, you know, actually, you know, the rate at which new surgical techniques have been developed has been really stymied in recent years, just because it's you know, we've kind of figured out that it's really unethical to try new things on people, right? And so, you know, one way that we can get around this is to actually use a virtual platform, right? And so the virtual platform that Finite Elements allows us to do is it allows us to try things like, you know, surgeries that we might not have thought of before, and to see how they turn out before actually trying that inside a real person, right? And so, you know, probably in the near future, you know, simulations like this might be kind of an important part of the approval process that, like, you know, the FDA or the medical boards typically go through. And so I will say that, you know, the technology isn't completely there yet, because, you know, the simulations, they're not able to factor in all the different complications that can occur, you know, but a virtual tool can still be a very valuable tool for these surgeons in order to try new things that they wouldn't be able to try on real people otherwise. Okay. Any questions on this so far? Okay. All right, and so from here, I'm going to skip around in the presentation a little bit, just to kind of, just because I want to cover the thing that's more relevant to finite elements. But, you know, a lot of these other slides, they cover, you know, things that I've done in my research. So I'll upload the slides after this, just so you guys can take a look. Okay, but I do want to fast forward to, you know, this specific research project that I had, which is based on the thoughtful selection of computational modeling techniques. Okay. And so I kind of want to bring this figure up again, just to kind of remind you that, you know, running a deformable wall simulation is something that's really important for these types of models. Okay? But which deformable wall model and how we actually perform this multi-physics thing is still actually a topic of intense debate. Okay. And so the general class of methods that are used to run these kind of multi-physics simulations is known as fluid structure interaction, and oftentimes we shorten this to be as FSI. Okay, and so FSI simulations, when you compare them to rigid, they're going to compute the wall deformation, and so that's the first thing. So instead of having zero wall deformation, now we have, you know, some wall deformation. Okay. The next thing that they'll do is that they'll allow you to model what's known as pressure wave propagation, right? And so what that means is that pressure waves can now travel at a finite speed within your cardiovascular system. Because if you have rigid walls, it's almost as if you had kind of a rigid rod, right? And so for a rigid rod, if you kind of tap the rod or you kind of flick it, that wave kind of propagates through the rod at kind of infinite speed. So the other end of the rod feels that ping right away, right? But if you compare that to say if you have like a jump rope, like a flexible rope, you kind of did like a wave on that rope, it takes a little bit of time for that wave to kind of reach the other side of the rope. Okay, and that's a direct result of the fact that the rope is a flexible structure, right? And so it's the same thing for blood vessels. So when you have a deformable wall, information about pressure waves, they don't propagate through your system at infinite speed as if they do in the rigid wall. Okay, right? And so the other thing that will happen is that when you run FSI, it'll affect the wall gradient. So when you compute things like the wall shear stress at your vessel walls, FSI is going to affect those computations. Okay, and so the thing with FSI is that there's multiple different methods, and so it's still an intense subject of research interest, and everyone has their own method that they developed, right? And so it's kind of annoying because everyone wants to be the developer of that one method, right? But what's kind of missing in the literature right now is a comparison of these different methods. So everyone's kind of developing their own method, but then no one kind of compares them against each other to see which one's better or not. And so that was kind of the motivation for this project, was that we wanted to try out in this case I only tried out 2 different methods, but we wanted to compare them against each other to see how they performed. Okay. And so the first method that I want to go over is called the Arbitrary Lagrangian-Eulerien. And so the shorthand for this is called ALE, right? And so ALE, without going into too many of the nitty-gritty details, people call ALE kind of like a true multiphysics experience. Okay, and so it's called true multiphysics because we have kind of 2 equations that we're solving at the same time, right? And so on the top right here, we have our Navier-Stokes equation. So this is our typical equations for fluid flow. Okay. We have one small difference, which is this guy. So this normally isn't here, but that has to do with the fact that we're doing an FSI simulation. So this is called a grid velocity, right? And so we're going to solve that Navier-Stokes equation in our fluid domain. So basically wherever there's blood. And then for the vessel walls, we're going to solve a different set of equations for a hyperelastic solid. Okay? And so this equation that I have right here, this is a differential equation for the vessel wall. Okay, and so I call this kind of a true multiphysics framework because we have literally 2 different equations that we're going to solve for at the same time. Okay, all right, and so this last equation that I have here is what's called a constitutive model. And what this tells us is kind of the stress-strain relationship for a hyperelastic solid. Okay? So I'm using a fairly standard one, which is called the St. Bernard-Kirchhoff model. And basically, we're plugging this S function in for this S right here. Okay. And so one other thing is that since this is going to be a moving domain simulation, so since our wall is going to be actually moving, we need to smooth out some of the distortions in our mesh. And so the way we do that is we solve a Poisson equation. Right? Okay, and so where ALE is kind of like a true multiphysics framework, another framework that we can use is called CMM. So CMM is kind of I don't want to call it like a watered down version because I think that's a little bit unfair to it, but it's not really a true multiphysics framework. Okay, and so the reason for that is because we only just have one equation that we're solving for. It's just that that one equation, we're going to make slight modifications for it in order to account for the deformable vessel wall. Okay, and so what I have right here this is our typical fluids equation. So this B fluid right here, this is kind of the same as our Navier-Stokes that we have here on the previous slide, except to that we're going to add some additional terms here to account for the vessel wall. Okay, and so because we're only solving one differential equation, this is a lot more computationally efficient. But it's not as robust. Okay? And so basically what the authors of this method basically says was that it's only reliable for displacements that are less than 10% of the vessel radius. Okay. Okay. And so one other factor that I wanted to take into account in this project was this idea of the pre-stress, okay? And so what I mean by that is, you know, typically when you construct your geometry from the image data that I talked about before, you know, that geometry there is already kind of stressed from the vessel wall, right? Because that's a live image of someone's, you know, blood vessels in action, okay? But what tends to happen is that, you know, when you run an FSI simulation, what it assumes is that the initial geometry that you start with is stress-free, okay? And so what tends to happen is that once you run the simulation, then your geometry tends to kind of inflate a little bit. Okay? So in this top figure here, what I have here is on the bottom, or in the underneath right here, I have the white geometry. And so that white geometry is kind of exactly what we extracted from medical image. And then this kind of red mesh that I'm layering on top, this is the geometry that we obtain after running the simulation a little bit. So you can see we have this kind of natural inflation that takes place because we assumed that our original geometry here was stress-free. And most of the time that's not the case, because that geometry that we're starting with actually has some stress, okay? And so in order to account for this, we actually need to solve for this, what we call the pre-stress, okay? And so if we account for this pre-stress, then, you know, we kind of get rid of this inflation phenomenon here. So we start with the geometry, you know, that perfectly matches, that kind of overlays with our, you know, medical image data, okay? Okay. And so what this slide here kind of basically summarizes the algorithm for which on how we solve for this pre-stress, okay? And so it's actually an iterative process, so it's not something that we can just solve outright, okay? And so the first step for this pre-stress process is we're going to first apply, we're going to run a rigid simulation. And so we're going to run a simulation basically with a rigid wall, okay? From there, we're going to extract the tractions. And so those are basically the forces that are being applied on the vessel wall, okay? From there, we can apply these as kind of like an external force. So we can basically apply them as a Neumann boundary condition on our vessel wall. From there, our model is going to displace, right? So just like you know, our typical finite element simulations, right? And so ideally, you know, once we compute these displacements, it should be something that's really small. So we can check basically the magnitude of all these displacements and check that they're less than some tolerance, okay? And then of course, you know, the first time that we run this, you know, this is not going to be the case. And then so from here, we can compute the stresses, okay? And so this displacement field is going to cause some strain in the vessel wall, which is going to cause some stress, okay? And so from there, we can compute the stresses, right? We can then add those stresses to the pre-stress, reset our displacement, and then kind of run through the same thing. So, you know, with our pre-stress, we can then apply, you know, our tractions, right? And then after we apply our tractions, our resulting displacements here should be less because we have this pre-stress that's applied onto our model, okay? And so from there, we can check again and then see if it's less than that. And if not, then we can kind of just keep continuing on with this algorithm. And so eventually what you'll get is a stress field for the vessels that we can kind of directly always apply, and that will be the pre-stress. Okay, and so from there, you know, now that we've kind of defined our methods, now we can kind of perform the comparison. So I basically kind of have 4 different use cases. Oh, I guess my cat's not happy with that. All right. And so our 4 different use cases are going to be using our 2 different methods for FSI. So our first method was ALE, and then our second method was CMM, okay? And then we can basically try both of those methods with and without the pre-stress, okay? And then we can run our simulations and then, you know, see what the results look like, okay? And then I'm going to try out these methods on 3 different geometries. And so the first geometry here is going to be simply just a cylinder, okay? The next geometry is kind of a 1 step up from this. So this is kind of the first, you know, a relatively simple cardiovascular geometry, which is just your aorta that goes down to your legs, okay? And then what I have on the right here is an interesting model, which is actually the result of a surgery done on a little kid, actually. So this was a kid that was born with a heart defect. And he had to get surgery in order to make sure that, you know, he can pump blood effectively throughout his body. Okay? And so this geometry that you see here, you know, most people don't have this geometry in their bodies, but, you know, this was something that's unique for that kid, you know. And then we were running simulations on it to basically see if we can, you know, if we can improve this kid's quality of life. Okay? But for this project, I just used it as another geometry to kind of test my 4 different methods. Okay. Okay. And so here are some of the boundary conditions and the statistics for the mesh that I used, okay? And so what I want to draw your attention to here are the number of elements that I use here. So as you can see, you know, these element counts are a lot larger than probably what you're seeing. You know, first of all, you know, it's going to be way bigger than the amount of elements you're using for your project. But, you know, it's also way bigger than what we can use in ANSYS as well. So, you know, to run these simulations, I use kind of a specialized research software. And so, you know, because of that, you know, I could crank up the element count to be much higher than ANSYS can handle. Okay, so you can see here I have element counts in the millions, or at least in the 100,000s. Okay, excuse me. And so normally, you know, we wouldn't be able to get this with ANSYS. Okay, and then from here, you know, you can see the other boundary conditions that I apply. Okay, and so first let's look at the starting geometries. Okay, and so on the left right here, I have the starting geometries from CMM and ALE. But these are the cases without pre-stress. And on the right here, I have you know, the corresponding results, but with pre-stress. Okay? And so you can see here, you know, when we don't apply pre-stress, you know, we have this kind of inflation effect, right? And so you can see that that kind of the general volume of the simulation results, which I show in color, you know, those are generally bigger than the original geometry, which I show in white. But once we apply the pre-stress, you know, those simulation results hug the geometry a lot better. Okay? And so you can see, you know, in both CMM and ALE, you know, the pre-stress was something that was, you know, that was really important for us to account for. Okay. And so the next thing that we can look at is the wall deformation. So this is basically a measure of how much the wall itself was deforming in our simulations, right? And so you can see here, you know, we kind of see the same trends. And so when we apply the pre-stress, which we show in kind of blue and purple, you know, we get a much lower amount of deformation than if we apply the pre-stress, or if we neglect the pre-stress. One other interesting thing to note is that, you know, for the cylinder case, you know, we had, you know, the red and green curves, they kind of overlap with each other. So, you know, that means CMM and ALE got relatively the same results. But, you know, for the aorta, there was actually some mismatch in between them, right? And so what happened was the CMM model actually overestimated the displacements a little bit. And the reason for that, remember, is that CMM is only reliable for, you know, relatively small displacements because it's not really a true multi-physics framework. Okay? And so when you use kind of a true multi-physics framework, you get kind of a little bit more modest deformations, you know, that generally are seen as a little bit more reliable than CMM. Okay. Okay, and so the last thing I think we'll look at is the wall shear stress. So these are kind of the distributions for the viscous shear stress that we talked about before. Okay. And so you can see, you know, the different methods and the different, you know, whether you use pre-stress or not, kind of have a big difference on the wall shear stress distribution in our models. Okay. And so the red areas here, they denote basically areas of high wall shear stress. So those are cases where, you know, we have a high amount of viscous shear, whereas the blue areas here are where there's relatively low viscous shear. Okay. And so you can see here that, you know, if we don't apply the pre-stress, you know, we have kind of much lower distributions of wall shear stress. But when we apply the pre-stress, you know, these actually look pretty similar to each other. So that's actually encouraging to look at. Okay. Okay, and so the last thing that we'll look at is just the relative computational cost, right? And so this basically shows the amount of computational hours that it's going to take to run these simulations. Okay. And so the big difference that I want to highlight here is that, you know, when you're running ALE, which is a true multi-physics framework, you know, you're going to pay a lot of cost for this, right? And so what this basically tells you is that I basically run my rigid simulation and kind of normalize this to have a coefficient of 1, right? And so running an ALE simulation for the cylinder, you can see it takes over 16 times as long as the rigid simulation. So that's huge, right? And so, you know, in order to run an ALE simulation, you have to wait 16 times longer than you would for a rigid. Okay? And so for the CMM, because it's not really a true multi-physics, you know, you can knock out those simulations a lot faster. And so the cost increase is less than 3. So so you still incur some cost increase, but it's not nearly as severe as if you're running an ALE simulation. And so, this is just kind of a way just to illustrate to say, if you do want to run true multiphysics, you kind of have to be prepared to pay for it in terms of time or computational cost. Okay, and so that kind of brings me to the conclusion. And so, hopefully what this presentation showed you was kind of a very, hopefully interesting application for finite elements. So just to show you that finite elements is not just limited to structural problems or heat transfer problems. So it can be used to solve, fluid flow. And in particular, in this case, a biological problem, okay? And so with that, we can answer a lot of questions that, may not have been able to answer before. Okay. And so with that, I'll end my simulation here. So I'll end my presentation here, and then we have 5 more minutes for questions if you guys want to ask. Okay. All right. So are there just any general questions about just this research or just anything in particular that that you guys want to know? Okay, so I see I have some questions on the project, so I'm happy to answer those. But Fernando, answer your question just briefly. So this was a PhD. This is my PhD dissertation, basically, or part of it. And so this is a PhD level research paper. Okay. So if there's no more questions, I'm going to go ahead and answer Eric's question here. Okay. So let me open up starter 3. Okay, so Eric wanted to know how do we call the an example of how to call the Gauss points in part 3. Right? Okay, so Stephen, I'll get to your questions after after Eric's questions. Okay. Okay. And so for part 3, the Gauss points that you're going to be applying are for the Neumann boundary condition. So actually, they're going to be the Gauss points for the. Okay. So should they be specifically defined, or should they be in variable form to calculate the shape functions? And so actually, I gave you the Gauss points actually in the project specs. So we go back here, and so if you go on page 7 of the project specs. I gave you the Gauss points for here, right? And so these, I gave it to you in kind of a variable format here, in kind of a coordinate format here, but you can plug those basically directly in here. And so these are basically going to be your xi and eta values for your code. Okay? And so let's take edge 1, 2 here. So the first Gauss point is going to be this location here, right? So if you do xi1 and eta1, right? And so the way we're going to do this is we're just going to basically plug in that expression here. So it's going to be square root of 3 minus 1 divided by 2 times square root of 3. Okay. And so that's our xi1 right here. And then our eta1 is going to be square root of 3 plus 1 divided by 2 times square root of 3. And so I just basically copied that that coordinate there. And then from here, I can do the other point. So the other point is given by this expression right here. And so we have xi2 is going to be square root of 3 plus 1 divided by 2 times square root of 3. And then eta2 will be the second expression there. So it'd be square root of 3 minus 1 divided by 2 times square root of 3. And so those are actually the xi and eta values. And so once you have that, then from when you're down here, you can actually just plug them into our regular shape functions. Okay? And so our shape functions for the triangle, they're going to be the exact same that you used for part 1 and part 2. And so like n1 is going to be xi. N2 is going to be eta, and then N3 is going to be 1 minus xi minus eta. Okay, right. And so here, you can see that I have 2 different evaluations for this. So I have the evaluations of the shape functions at Gauss point 1, right? So these would use xi1 and eta1, And then I have the evaluations of the shape functions at Gauss point 2, so xi2 and eta 2. Okay. And so so I guess to answer your question, you would use the same shape functions. It's just that the variables that you plugged into there will be different because you're evaluating them on these lines instead of in the interior on the element. All right, so Stephen, to answer your question really quickly, part 1 and part 2, they have graphs they have figures that look similar, but they are slightly different to each other. So they look similar, but they're not quite the same. And so actually, the real litmus test to really tell is that if you take your part 2 and then you plug it into part 3, and you're not getting the right answer, then that's kind of a way to tell that you need to fix part 2. Yeah. So they look similar, but they're not quite the same. So there's kind of subtle differences in them. Okay. And so with that, we're out of time today. So so thank you everyone for tuning in, and thank you everyone for a great semester. So I know I asked a lot for you guys, and I know that this class was a lot of hard work, but I really appreciate you guys putting in all the hard work. And what I hope is that you take something kind of useful from this class, and you take it on for your future careers or anything like that. So just for the final time, I guess we're going to sign off. And so I want to tell everyone to stay safe, stay healthy out there, especially in these challenging times, and have a great, happy holiday season, and I'll see you around when I see you around.
Thank you, Professor.
Thanks, guys. Thank you. Thanks, guys. Did you guys have any more questions? Okay. So if not, I'm going to go ahead and sign off. So thank you guys again for coming. Have a great winter break. And if you have questions on the project, definitely don't be afraid to reach out. Okay.